All right, welcome to another video shot from Mr. Westphal's house. Hope you're doing well. This video, merge sort, right? We're going to talk about um, the efficiency. That's a main part of this is to figure out the efficiency of merge sort. But then we'll talk a little bit about like what the code looks like. Again, with the idea on the AP test, you're going to have to interpret it, not necessarily write or generate the merge sort code. If you want to try and write the code yourself, that's a great challenge. Um, but yeah, we're going to go through it a little bit and then do the timing efficiency of it, right? Particularly comparing to our other two sorts, insertion sort and selection sort, figure out which one is the best. Okay, so this was on the assignment from yesterday. So this is the code, part of the code actually for merge sort, where we merge the two lists together. And I just want to blast through different parts of it here. And I'm mostly going to talk through it because it'll be hard for me to write on this, but at any rate, hopefully you had a chance to look at this ahead of time. So this first thing is just making a new array that's combines the length of the two coming in. So if we have like 4 elements here and 3 here, then we're going to need one that's got 7 spots when we merge, right? Because we're going to take the stuff from these two lists and merge them into one. Okay, and then the way, I think this is probably Mr. Westphal code here by the looks of it, not necessarily AP, but I do an index for where we are, right? Because remember that we kind of go through and compare whatever spot we're on and take the smaller of those two spots. And so that process, we track the indexes, right? Which we start off in position 0. So if we have like this sorted array, let's say, and we're merging it with 4, 12, 15, you have the different indexes, right? You have an index like IDX, list 1 index and list 2 index that keeps track of where we are in the comparison process. All right, and then this new IDX I just made to track where we're putting it in the array, right? Because we have this new array, which in my example here has 6 spots. Wow, that's a terrible drawing. See if I can draw it a little bit better. But it'll have 6 spots, and so we have to track where do we put the next one. Sorry, my computer glitched there. So we have to have a thing that tracks where are we in this list of inserting, right? Where are we going to put? So like basically this one here, get my grabber here, this one, where are we going to put it? We're going to put it there. Man, that's bad. Sorry. I think it's glitching a little bit. Technology issues. But at any rate, this one again goes in spot 0, and then the 4 will go here, and then the 5 will end up going here, right? So we have to keep track of where they go. Okay, so basically we say while neither list is like emptied, right? So these indexes, while they're less than the length, while neither of them emptied, we want to say if the one in list 1 is smaller, then we're going to add that one to the new array, and then we're going to increase both of the indexes. So going back to the visual here, it's probably the best way for me to explain it, is we start off with our indexes here and here and here, where those dots are, and then we need to move over. Once we insert the 1, we want to move this index over 1, and we want to move this index over 1, right? Which is what you see in this code. Okay, and if it's not less, then we're taking from the other array, and so basically we add from that array, and then we move over those indexes. Okay, and so this while loop runs while both of them haven't been like completely exhausted. But then once, so like in this example here, once we exhaust this first list, then we can just spin through and whatever we have left over in the other list, add them to the end. So in this case, the 12 and the 15, let's get added to the end once we emptied the first list. Okay, so down here we have 2 more loops that say basically if there's anything left, neither one of those arrays, then just spin through and dump them in by increasing the indexes of whatever list we're taking from. Okay, and then obviously we return the merged array. All right, so that's probably the hardest part is merging the arrays there. And that's some pretty tricky code, especially because we got all these indexes. But it comes from, we sort of have 3 lists, the 2 are merging, and then the result merged list. Okay, so the other piece of the code here, this is the high level sort view of it. And basically, if we walk through, I'm going to pause this again and see if you can figure out what is each step, right? And so I think I put this on here. So here's the merge sort, basically is recursive. It splits the elements in half, calls merge sort on the bottom half, merge sort on the top half, and then merges those results. Okay, so this merge sort is actually a recursive method. And so see if you can spot these steps in this code. Pause the video and see if you can figure it out. Okay, so you can see our array, our method is called sort, and we're going to recall it. So basically, this is our base case. So if we get down to just one element, right, length less than 2, we just return the list, right? So if it's got one element, we return the list. Otherwise, this part is all split. So this is going to split it into 2 mini arrays. We make an upper and a lower half, create their sizes, and then this would like copy them into the upper and the lower half. Okay, and then here's where it sorts the lower, so it's recalling the method. Again, and recursively, and as long as our length is greater than 2, we'll keep calling it recursively, greater than or equal to 2. So it merges the lower half, or sorry, sorts the lower half, sorts the upper half, and then it merges those two together and then returns that merge copy. Right, so this actually combines the last two things we've been doing, sorting and recursion, and it's pretty complex. All right, so today, then the rest of this is just to do the efficiency of merge sort, especially compared to our other ones, which are n squared. So that'll be the main part of this lesson. Okay, so to do merge sort efficiency, this is actually going to be the exact same thing as we did for insertion sort and selection sort. So you're listening to new file, right, from the starter code. Again, same spot as you got them before, except we did sort, timing of insertion and selection. So now you just need the one called merge sort timing and put it in the same package. Make sure you have the array utility there and then the stopwatch, which will be needed to time it. All right, and so it's the exact same thing as before. You're going to make a table, and you're going to test sorting 10,000 items, 20,000, 30,000, 40, 50, 60, and then time how long it takes. Okay, and for comparison purposes, here are my selection sort times. So I don't know if you still have yours. You can compare against them. If you don't, you could always just rerun it, right? It takes like 2 seconds to rerun it. Just there's your selection sort timer, run it, and then compare it to the merge sort. So just to make it as clear as possible, right? Here am I in Eclipse. Here's my timing folder. I have all my files that I need. And then merge sort, I just start off with 10,000, right? It really doesn't matter what, I don't think it matters what you pick for the max item. You can mess with that if you want. But at any rate, I'm going to do 10,000 and time it. And you can see it's running pretty fast. Again, it's a little goofy because I got all this other stuff running. But I'm just going to put that down. I'm going to say it's like 100th of a second, right? So run it on your computer because it'll likely be different, right? And then all I got to do is go back in, change my number of items to 20,000 this time instead of 10,000. So we double it, and we're going to kind of see what happened with the time. Is it going to double? It's going to more than double. All right, and not going up a whole lot. Wow, that's a pretty big difference between my times there. So I might run it a bunch. That one seems like an aberration. So I don't know. That seems like a good one. Not to make it exactly linear, but just somewhere in the ballpark. Okay, and just get a rough average, and then do it for all of these, and then use the decimal thing to graph them. Right. So I'll let you fill in the table first, and then pause it, come back and watch if you forgot how to do it on decimals. Okay, so I actually went back and looked at last year's numbers, right? Because I feel like my numbers now aren't accurate because I'm running this video recording software and stuff, so my computer is all out of whack. But at any rate, these are my numbers from last year. You can see what you got. And then we're going to make them on decimals, right? So I'll walk you through how to do that one more time if you're not sure. If you already know how to do this, you can kind of skip over this part. But at any rate, I'm going to add a table from over here. And then I'm going to type in my numbers, 10,000, 20,000. And Decimal starts to add them in for you, which is really slick. Right? And then just enter my times from the tables. So I'm going to pause here and just whip through. So they're all in there, right? But nothing shows up. So I just need to make my scale again right? So it'll hit the little wrench up in the corner, and my x's obviously need to make these pretty big. So I'm going to go from 0 up to 70,000 based on my x values and my y values. I don't really need to show the negatives, but I'm just going to show up to about, well, that's not very much, so maybe I'm just going to do 1 even, right? And then I'm going to scroll it around here and see. So you can see, based on that, it is not, the other one was a squared one, right, where we kind of had this squared curve. Certainly not the case here, right? This looks pretty flat, pretty linear. So as n gets big, the time is much, much more efficient, right? And so this is actually a huge win, right? So when we're talking about our different sorting methods, this is where Google and those other companies are so much smarter than everyone else, because this is super less amount of time, right? It's an incredible difference compared. And if we started to get really big, like if we had 100,000 or 200,000, the difference is even more and more pronounced, right? So I think the best way for me to explain that, obviously, is just to look at some of the graphs. All right, so here's selection sort, the n squared compared to merge sort, right? And you can see as we go up in items, it's quite a bit of difference, not in the beginning, but as we get lots of items, it makes a huge difference. Okay, and here's just another picture of it. Sorry, this didn't show up completely. I can move it all the way up. Right, so it's the number of elements and then how many comparisons or how much steps it takes. And you can see n squared goes up quite a bit faster. All right, and what we're actually going to find here in a second is for, if you want to try big O on your own, give it a shot. It's pretty tricky, but if you want to try, before I give it the answer away here, what we'll find is actually merge sort is an n log n1. Okay, and so this, if we just take, say, even 10,000 elements, right, the comparisons for an n squared is 10,000 squared, which is a pretty big number, but that is quite a bit smaller than if we did, say, 10,000 times the log of 10,000. That's going to be quite a bit less than 10,000 squared. And again, that gets even more and more pronounced as n gets big. In case you want to see the specific math of it, here's the difference, right? Merge sort is actually a log base 2, which I'll get into here in a second, but you can see that the number of comparisons, even at 10,000, is quite a bit different between an n squared and n times log n situation. So where do we actually get this log base 2, right? So to do the big O analysis of this a little bit, the log base 2 comes from, that's how many levels we end up having. So if n is 4, so say we had 4 items here, we'd have to split once here and then split a second time there and there, right? So that would just make two levels when there's 4 items, right? And then when you're 8, you have to do a split in the middle, one extra split, and then it's the same because it's 4 and 4. So we do a split, a second set of splits there, and then they split up the 2 here, here, and there. Okay, so with 8 items, it's just one more level, right? And similarly with 16, you can just imagine we'd have to have one more split to get it to 8 and 8, and then it would be the 8 case, right? So basically, to figure out the number of levels here, you just do the log base 2 of whatever n is, right? So that's where the log base 2 comes from. Right? And then when we're merging them back together, for each level of the merge, right, it takes n comparisons, roughly, right? Because, I mean, it's a little bit less than n actually, but you have to compare these two, right? So when you place these, sorry, it'd be 2 there, 9 there, 3 here, 4 here, 0, 1, 6, 9. I guess those are mostly in order. And then when we merge these, for each time you place a number, you have to compare. So here we're comparing the 2 and the 3 to place the 2, and then we're comparing the 3 and the 9 to place the 3, and then we're comparing the 4 and the 9 to place the 4. Okay, and same thing here. When you place each one of these, you have to compare one time to place each number when you merge those 4 together. Right, and same thing when you merge these together, then for each time we have to compare a pair of numbers to put one into the merged list. Right, so basically, since there's n numbers, there's about n comparisons each time to place them. Right, technically this last one's probably like n minus 1, but in general, you have, I'll give you your summary down here at the bottom.